Welcome everyone in this NPTEL online certification course on biological process design for wastewater treatment. So, in the previous lectures we studied regarding the wastewater treatment and some of the unit operations that are carried out for treatment of such wastewaters. Now, we started learning about the first step, that is the flocculation, and thereafter the aeration in the previous lecture. Now, we will be continuing further and we will be studying regarding coagulation, flocculation and sedimentation. So, we will start with the introduction section of this. So, we generally carry out coagulation and flocculation for two purposes. One is to enhance the size of particles so that they will settle down in a reasonable period of time. The objective is to settle the particles which by themselves do not settle down, and they should also settle in a very reasonable period of time, so that the design of the coagulation flocculation system requires minimum volume possible. So, for doing this we use coagulation and flocculation with effective doses of coagulant and flocculant if required, and also we take care that the what types of particles are there, what is the size, what is the zeta potential on the particles. So, all these terms are very important when we are studying coagulation and flocculation. Once the particles are settled and precipitate are formed, they settle down, and most common methods of removing them from water is by gravitational settling in a sedimentation basin. So, that is why coagulation, flocculation and sedimentation, they are generally performed in sequence, and the unit operations are in sequence. Now, studying further, coagulation and flocculation units are used for removing non-settleable suspended solids or particles within some time domain present in the water. So, we want to remove the non-settleable suspended solids or particles which by themselves do not settle down, and the reason may be that their density is smaller or their size is very smaller. So, if any of these two factors are present, that the density of the solids is small and or their size is small, they will not settle down. So, they are within some limit, their size is within some limit. So, it cannot settle down by itself, and similarly density is also smaller if possible. So, then also it will not settle down. Now, to remove these solid particles may be infectious. So, we can remove these infectious agents. They may be toxic compounds also, and they can be removed via adsorption to the surface of the particles which are formed via coagulation coagulants. So, we can remove toxic compounds, we can remove infectious agents, and we can remove precursors also which lead to the formation of disinfectant byproducts. So, through this we can remove all these materials via coagulation and flocculation. So, during coagulation, chemicals or coagulants with charges opposite to those of suspended solids are added to the water to neutralize the negative charge on the non-settleable solids such as clay, color producing organic substances. So, what happens is that in the colloids which are present in the natural water, suppose this is one of the colloid. So, generally at its natural pH in the water and wastewater, it will be negatively charged. So, this will be negatively charged. Now, there is another colloid which is again in the same water and which is of size similar to that or maybe little bit different, it is also negatively charged. Since both are negatively charged, so there is always a force of repulsion between them, and since their sizes are also small, they cannot settle down. Now, what is done is that we will add some coagulants which have charges opposite to those of suspended solids. So, that means we will be adding some coagulants which will impart positive charge, like suppose alum sulphate is there. So, from alum sulphate Al3 plus will come out. Now, this Al3 plus, that means it is positively charged overall. So, this positive charge will be attracted and it will go to the surface of these colloids, and thus the charge of the colloid is neutralized. So, here we neutralize the negative charge on the non-settleable solids. So, thus since both are now neutral, and if we can somehow force them to come together, then van der Waals force of attraction will come into picture and they will form a bigger flock which will be combined together. And now since both are virtually neutral and their size has become greater, so they have lot of probability of settling down. So, this is what is done in the coagulation. So, we always add coagulants with charges opposite to those of suspended solids present in the water. So, this is the idea. Now, once the charge is neutralized, the small suspended particles are capable of sticking together as shown in the previous slide. Now, rapid mixing is done to properly disperse coagulant. So, as soon as suppose this is a water tank and as soon as the coagulants are added, so they will break into respective positive and negative side. So, what is done is that we do rapid mixing so that the coagulant disperse all throughout the solution. Now, and also through rapid mixing we try to force the coagulant to reach out to the negatively charged particle, so that it may be neutralized. So, this rapid mixing is done to properly disperse coagulants and promote collisions among the coagulants and suspended particles to achieve good coagulation. Over mixing does not affect coagulation, but insufficient mixing will leave this step incomplete. So, up to charge neutralization we try to do using the coagulation step. After that we have flocculation step. So, a gentle mixing stage which increases the particle size from sub microscopic microfloc to visible suspended particles. So, this is done. So, in this case what we do is that we try to do the gentle mixing. Now, since two colloids have come together, we want the third colloid to also come and form a bigger flock, but we do not want very rapid mixing, otherwise these flocks may separate out. So, that is why only gentle mixing is done. Gentle mixing increases the particle size from sub microscopic microfloc to visible suspended particles. These microfloc particles collide, causing them to bond to produce larger visible flocks. This flock size continues to build up with additional collisions and interaction with added coagulant. Once the flocks have reached the optimum size and strength, the water is ready for sedimentation and then they will settle down in the sedimentation stage. Some other flocculants are added also which help in increasing the size. So, this will depend. You can refer to the another of my lecture on physico-chemical methods for wastewater treatment, where I have discussed the coagulation and flocculation in detailed, so that you can further study these topics. For this biological process design, I think this is enough. Now, further going on, sedimentation theory. The settling particles of the particle could be categorized, properties can be categorized into 4 classes. So, settling, once it is done, settling in the is done after coagulation, flocculation, after biological treatment also, that is called secondary settling, and then some other places also settling is possible during treatment itself. So, sedimentation or settling is very important, not only for physico-chemical treatment, but for biological treatment also. Now, settling properties of particles can be categorized into 4 categories. One is called discrete particle settling, then flocculant settling, hindered settling, and then the compression settling. And what is the difference between these 4? So, discrete particle settling, as the name suggests, here only suppose this is a beaker is there. So, we have only few particles which are settling down and they are not affecting each other. So, we have discrete particle settling. So, generally we start the theory using the discrete particle settling. Then we have flocculant settling, where the particles are coming together and forming bigger flocks, and then they are settling down. So, this is flocculent settling. In the hindered settling, the amount of particles are such large that they actually affect the settling of each other. So, this is hindered settling, and in the fourth stage compression settling, the amount of particles is much larger, that particles themselves compress the particles which are at the bottom, and thus the settling occurs. So, which we have compression settling. In actual settling time, it is not uncommon to see all of these type of settling may happen. The design of ideal sedimentation tank, one of the controlling parameter is the settling velocity of the particle to be removed, and this theory can be obtained from the discrete particle settling itself. So, we will try to study sedimentation or settling in detail, because it is very important for our course. Now, types of gravitational settling phenomena. So, we can have discrete particle settling as suggest, applicable for very low concentration solids. Particles settle as individual entities, no interaction occurs between the particles. So, this is discrete particle settling. Then we have flocculation settling, applicable for dilute suspension of particles that coalesce or flocculate. By flocculation, the particle size increases and the terminal velocity also increases. So, settling can be increased by addition of some ballastic agents such as polymers or some other flocculants also. So, this is possible. Then hindered settling, for suspensions of intermediate settling. So, this is hindered settling, where for suspension it is used. In this case, the particles are such close together that the interparticle force due to one hinders the settling of the another particle. So, that means we have lot of particles, and the settling of one is actually affecting the settling of another. The particles remain in the fixed position with respect to each other, and particles settle as a whole. This is the hindered settling. Then we have compression settling. In this case, the particles are set in such high concentration that the whole structure is formed, and compression takes place due to the weight of the whole mass, which continuously increases. The clear water is formed above the compression zone. That means, the clear water is above and all the settled particles are at the bottom. Now, we will start with the first in greater detail, the discrete particle settling. That discrete particle settling sedimentation is characterized by particles that settle discretely at a constant settling velocity. They settle as individual particles and do not flocculate during the settling. Examples like sand, grit, etc., or a mixture of abrasive particles that may include sand, broken glass, etc. The only application of discrete settling are due to pre-sedimentation for sand removal prior to coagulation in a potable water plant, or in settling of sand particles during cleaning of rapid sand filters, or in grit chambers, etc. Now, but with the discrete settling, we have the particle settling theory, and this is very important, because it helps us in designing the settling or sedimentation basins later on. So, we have a particle settling theory which is based upon the discrete particle settling. So, when particles settle discretely, the particle settling velocity can be calculated, and the basin can be designed to remove the specific size particle. Suppose a particle is settling in a fluid, then under that condition it experiences following forces. So, this is the particle which is settling down. Now, suppose it is settling down at the bottom, so it will experience a force in the same direction, which is labeled as Fe, but this is, suppose this A is equal to gravitational force of gravity. So, this is actually Fg, the force of gravity. Now, since the particle is settling down, there will be a buoyancy force which is opposite to the settling. So, this buoyancy force will be going towards upwards direction, and this Fb is called buoyancy force. Then there will be a drag force also, which will be dependent upon the velocity with which it is settling down, and this is a drag force which will be acting opposite to the settling direction. Now, overall the force balance can be written like this: m du by dt is equal to F e, which is downwards, minus F d minus F b. So, F d is the drag force and F b is the buoyancy force. So, and m is the mass of the particle, u is the settling velocity of the particle in the fluid, which is here given, and a is the acceleration force. This a can become equal to g for gravitational setting, equal to r omega square for settling under centrifugal action, but we will be considering mostly the gravitational settling. So, A e is equal to g, that will be there. Now, going further, the drag force and the buoyancy force can be given as follows. So, buoyancy force easily can be written as m into rho f by rho p into A e. So, rho f is the density of the fluid and rho p is the density of the particle respectively. Now, A e already we have defined. The drag force can also be defined like this: drag force is equal to C d into rho f u square by 2 into A p. So, C d is the drag coefficient, we will be learning regarding this, this is very important. Then A p is the projected area of the particle. So, for spherical particle we can easily calculate, otherwise we have to find out the sphericity and then we can determine. M is the mass of the particle and rho f is already defined here. Rho f is the density of the fluid, u is the settling velocity. Now, what we do is that we put the value of F d and F b in the previous equation. So, the equation becomes like this. Now, for spherical particles having diameter d p, the value of A p and m can be given as follows: A p is equal to pi d p square by 4, this is projected area, and mass can be calculated by using the volume into density. So, that volume is pi d p cube by 6 into rho p. So, we can substitute A p and m using this. Now, for particles settling with terminal velocity, suppose the velocity terminal velocity has been reached. So, under that condition du by dt will be equal to 0 and the gravitational force we are keeping A is equal to g. So, under this condition what we have is F e is equal to F d plus F b, and we will put all other values in this equation. So, if we put all the values and try to find out the, we keep also u is equal to u t under terminal velocity condition, and if we try to solve the equation we will be getting these two equations. In one of the equations we have kept as such, there is A p term, there is m term, okay, and there is C d term. In the second equation both are essentially same. This is for spherical particles, that means A p and m have been replaced for spherical particles. So, we have two equations. This is more common equation which is used, because generally what we consider is that the particles which are settling down are spherical in nature. So, this is spherical particles. So, this is the equation which is most commonly used. Now, in this equation there is a term for C d, and this is very important, that what is the drag coefficient, and because drag coefficient is dependent upon the velocity also. So, this is variation of drag coefficient with respect to particle Reynolds number. So, particle Reynolds number we can calculate using the velocity and other parameters, viscosity, diameter and the fluid parameters also. So, drag coefficient C d varies like this. So, C d is like it decreases linearly up to a certain range, which is around the particle Reynolds number of 1. So, up to this range or 1 or 2. So, this is linear. After that, in the later stages, when the Reynolds number, particle Reynolds number is greater than 10 raised to 3, this CD is virtually constant. So, it is fixed, it is a certain value which is fixed in between this. So, this first region where there is linear decrease, it is called Stokes law region, and in the case where the CD is constant, it is called Newtonian region. Okay. And in between we have transitional region, transition where different equations have been given to model the variation of CD with particles Reynolds number. Now, how these can be modeled? In the laminar region where the Stokes law is applicable and where the CD decreases linearly with Reynolds number, the CD is given as CD is equal to 24 by RA, and this is applicable for Reynolds number which is given, particles Reynolds number which is given rho f into ut into dP by nu f, which is the fluid viscosity. Now, if the Reynolds number is between 0.01 to 0.1, sometimes it is taken as 1 also. So, under up to this condition a CD is taken as 24 by RE, and this RE can be replaced by this term. So, overall the equation will become ut is equal to G rho p minus rho f dP square into 18 nu f. So, this is the equation which is used in the laminar zone. Now, we have a transition zone also and we have a turbulent zone also. In the transition zone various equations have been given, and this transition zone can be taken from 0.1 Reynolds number to up to 1000. Now, there are different types of equations, like one of the equation is CD is equal to A by RE raised to n, and generally A is taken as 18.5 and this n value is taken as 0.6. So, we can use this equation. Similarly, CD is also given, the drag coefficient is also given by this type of equation which is reported in the literature. So, we can use any of the equation depending upon the type of water, wastewater, etc. Then for turbulent zone there is another equation that for Reynolds number around 500 or from 1000 to 2 lakhs, we can take CD is equal to 0.44. That means CD is equal to 0.44. Now, if you take this equation and previous CD is equal to 24 by RE, we can generalize the value of CD. This equation can be considered as common for all three. Now, CD is equal to alpha RE raised to minus beta. So, this is the equation. Now, in this case for Stokes law range, we have alpha is equal to 24 and beta is equal to 1. So, that means it becomes 24 by RE. So, this equation is correct. Now, for Newton's law range, we have beta is equal to 0 and alpha is equal to 0.44. So, that means CD is equal to 0.44. So, this equation is correct. Similarly, for intermediate range, the alpha is taken as 18.5 and beta is equal to 0.6. So, this equation is generic equation representing the CD variation with particles Reynolds number. So, this equation can be used. Now, for non-spherical particles, the formula for Reynolds number and settling velocity calculations are modified using the shape factor psi, and which is for Reynolds number it is multiplied by psi, and here we add a term psi. So, this equation can now be used in place of other equation if we know the shape factor value. The shape factor may be 0.9, 1.1, 1.2. So, depending upon that we can find out the value of settling velocity. Now, in general, suppose we have to solve a equation for finding out the Reynolds number, and we for a discrete particle where everything is given. So, what we have to do, the general steps is that if go further we should know the different values. So, like first thing is that we should know the diameter of the particle. So, it should be known to us in micrometer or something. So, this should be known to us. Then we should know the diameter, the density of the fluid, or we can take this to be density of water. because for wastewater generally it may be taken as for water. So, this is density of water. Then we should know the density of particle also. So, this should be known. Similarly, we should know the viscosity of the fluid or viscosity of the water. So, this should also be known to us. So, suppose everything is known to us, all these 4 parameters are known to us. So, under this condition what we can do is that we have to find out the settling velocity. Now, since all these 4 are knowns, but we do not know the value of C d, because we do not have the value of, suppose shape factor is also known, for purely spherical particle it will become 1. So, now what is the value of C d? C d we do not know, and until unless we do not know the C d value, we cannot find out the terminal velocity. So, for doing this, what is done is that we try to find out the value of, we consider that the settling is actually happening in the laminar region. So, for starting the calculation, we assume that there is a laminar zone settling which is happening. So, that means we have the C d value is equal to, we are assuming that it is in the range of Reynolds number 1, or we can assume the this to be in the range of r is equal to 1, and we directly apply this particular formula for calculating the ut value. So, here as soon as we assume that laminar zone is there, we can directly use this particular formula, and once we are using this particular formula, we do not require the C d value because it is fixed. So, if we assume laminar zone, we can find out the ut using the equation which is given here, okay, and then we can find out the ut. Once ut value has been found out, we can find out the value of Reynolds number. So, once ut is known, we can, that means ut should be known, then we can find out the value of particle Reynolds number, and once particle Reynolds number is known, we can find out the value of C d, and since C d is known, suppose C d value comes out to be, this Reynolds number comes out to be in the range of any of these. So, if it comes out to be less than 1 or less than 0.1, that means our initial assumption that it is the laminar range is correct, and we can find out, we can be sure that ut is correct. Now, suppose it is possible that this Reynolds number is not in the laminar range. So, it is in the transition range or it is in the turbulent range, then we have to find out the value of C d, and from C d we calculate back ut. So, the first calculation is until unless this ut and this Reynolds number, they should fall in the same transition zone. So, that means the C d calculated assumed and the Reynolds number should be in the same transition zone, and we keep on calculating this because the Reynolds number will go on changing. So, this is the, if we write like this, this is the first iteration, then second, then third, fourth, because the Reynolds number will keep changing. So, C d value will also be keep changing, though they may be in the same zone also. So, this is done until the 2 consecutive ut values are same. So, this is the iteration procedure which is adopted for finding out the terminal velocity using the terminal velocity theory which has been given here. Now, the problem here is that we have to do lot of iteration and we have to continuously modify the value of Reynolds number and thus the value of C d until unless 2 consecutive uts are very similar, and that then that ut can be assumed. Now, this problem can be solved using the non-iterative method for determining terminal velocity. So, this is done. Initially this was the formula, if you remember, this is the formula which was there for ut. Here only difference is that we are using, so we have the terminal velocity which is given, and the difference here is that we are assuming, here it is being assumed that rho p is much greater than rho f, which is actually correct. So, if we multiply this equation by this, and then actually we get a term where the k value will be defined, the k value will be this. Now, suppose the C D is equal to 0.44 and we use this particular k equation. So, what we do is that this all these equations for different ranges will be modified. So, in place of C D we use the k term, and for Stokes law region the k value will be less than 3.3. For intermediate range the k value is greater than 3.3, but less than 43.6, and for Newton's law range the k value is greater than 43.6 up to 2360. So, this k value is used. Now, the using this k factor also, the Reynolds number, the equations for different ranges are also modified. So, this equation can be changed as follows. For less than 2 in the Stokes law region, it is the Reynolds number will be given by k cube by 18, and similarly for greater than 500 in the transition zone, Reynolds number can be given by this equation. Now, the beauty of this equation is that we do not need to perform the iteration. Once the values are known, like here dp, rho f, rho p, nu f, etcetera are known, we can directly find out the k value, and once k value is known, we know that okay, k value is in the Stokes law region or in the Newton's law region or intermediate region, because from k value we can directly find out the region, and once this is used we can directly go for finding out the respective equation, and from there we can solve to find out the value of the terminal velocity. So, this is non-iterative method of finding out the terminal velocity as compared to previous equation. So, with this we will end today's lecture, we will continue further. Thank you.